Time out of your day. Try that again. So thank you everybody for taking some time out of your day to find out a little bit more about what's going on with Greenbank Observatory and some of the cool science that's been going on with it. So I'm Karen O'Neill. I'm the site director of Greenbank Observatory. And today I'll give a little bit of news about what's been going on site the last few weeks. And after that, we're going to move on to a science presentation on NANOGravs pulsar timing data and some of the work that's been going on there. Ryan Lynch will give a quick overview of what's the NANOGrav group and what's the work they've been doing. And then we'll move on to the highlight, which will be Joseph Simon from University of Colorado Boulder, talking about the overall search for the stochastic gravitational wave background with NANOGravs data. So what's going on with the observatory is, as always, it's same as going on much around the country and the world. Certainly the number of COVID cases is on the rise fairly dramatically. Now within the state, we're about 5 to 6% of all tests, although we have a number of counties where the positive percentage rate for COVID is as high as 40 to 60%, so quite high. Fortunately, Pocahontas County, where Greenbank Observatory is located, has been spared some of the worst of that so far, although even within our county, the numbers of cases has been going up fairly rapidly. Looking forward to the Thanksgiving holidays that are coming up in the US. A lot of universities within the state are closing down and not reopening afterwards, so ending their semesters early. As a consequence, the schools across the state of West Virginia are also staying out of in-person school for at least a week after Thanksgiving to give time for things to settle down after everybody comes home. Within the observatory, of course, we remain in 24 hours a day, 7 days a week operation. Everything has been going fine, but slowly. You know, we certainly have a number of people going in and out of quarantine based off of what's been happening within their family lives and their local lives, but we still have no cases of work-related COVID-19 on site, which is fantastic. Looking at the GBT itself, the 21A disposition letters for proposals are coming out. So if you put in for a proposal, you should have received or should be receiving your disposition letters very soon. And the other big news, as I mentioned a couple weeks ago, we were going to be testing a new low-power radar system. This is a prototype, a proof of concept system. On the telescope, we did that last week, and the tests were quite successful. We're working on a press release, so I'm not going to show you any results yet. I don't want to scoop our own press release, but just to know that within the next couple weeks, you should see a nice press release, and certainly next one of these bi-weekly meetings, I'll be able to show you some nice results from that. Other things going on is our Education and Public Outreach Division has some limited opening this month. They have walking tours, demos, canopy lectures, and so forth. They're also continuing with a lot of their online activities. So if you can't come to Greenbank, which would be great if you could, do look online, look at our Facebook page, look at our web pages, and you'll see some of those activities. And just for a completely blatant advertising here, we also have our online gift shop open, and we're even going to have a Black Friday sale online next week as well for you guys. So with that as a reminder, the next Observer Training Workshop is coming up in February of 2021. This will be a virtual school. And please feel free to sign up online for that. And then the Single Dish Training School is being moved to the fall of next year. Sorry, that's fall of 2021, not fall of 2020. And it will be held in Greenbank with an option for virtual attendance if anybody cannot make it on site at that time. So with that, I just want to thank everybody again for their time and for spending a bit of time during your day to listen about Greenbank Observatory. And I will now hand this off to Ryan and Joseph.
All right, thanks, Karen. Let me share my screen. All right, there we go. So I'll just briefly introduce myself. I'm Ryan Lynch. I'm a staff scientist at the Greenbank Observatory, also a member of the NANOGrav Physics Frontier Center. And so I'm going to provide a brief overview of the NANOGrav project and the most recent data release before I hand things off to Joe Simon to talk a little bit more detail about some of the latest results. So for those who aren't familiar with it, NANOGrav stands for the North American Nanohertz Observatory for Gravitational Waves. And NANOGrav is an observatory. It is a gravitational wave observatory that uses pulsars spread throughout the galaxy as probes of space-time in order to detect, hopefully, the influence of nanohertz frequency gravitational waves at the Earth. NANOGrav's gravitational wave frequency sensitivity peaks in the nanohertz frequency range, which is significantly different from other gravitational wave detectors, such as ground-based laser interferometers like LIGO and future space-based laser interferometers like LISA. And that means that NANOGrav is sensitive to different source class. We expect that the dominant source class at these gravitational wave frequencies will be supermassive black holes, both a stochastic background, which is the summation of a number of individual systems, but eventually also individual black hole binaries. Although more exotic sources like cosmic strings and even primordial gravitational waves are possible at these frequency ranges. So by using a variety of different gravitational wave observatories covering the gravitational wave spectrum, we get a complete picture of the gravitational wave universe, much in the same way that electromagnetic observatories at different frequencies and wavelengths give us a complete view of the electromagnetic universe. So these are very highly complementary techniques. But in addition to being an observatory, NANOGrav is also a collaboration of over 100 full or associate members at now over 50 institutions. And there are also dozens of undergraduates that are involved. We are very proud of our track record of having young, successful early career scientists in leadership roles. 60% of the working group chairs within NANOGravs or postdoc or brand new faculty. And we also collaborate internationally with the European Pulsar Timing Array and the Parkes Pulsar Timing Array through an umbrella organization known as the International Pulsar Timing Array. And we're increasingly collaborating with similar groups in China, India, and South Africa. So I've used this term pulsar timing array a few times now. Let me explain that just a little bit more. Millisecond pulsars are our probes of space-time. We use them as clocks, and their ticks are basically the arrival times of pulses at the Earth. And we can use these as basically tools for a differential range measurement between the Earth and the pulsars. The influence of gravitational waves at the Earth is expected to cause path length deviations of about tens of meters, and that corresponds to tens to hundreds of nanoseconds changes in the arrival time of the pulses at the Earth from what we would predict in the absence of the influence of gravitational waves. Now, one of the key features of this is that we expect a very particular spatial correlation pattern between pulsars, which arises from the quadrupolar nature of gravitational waves, which is predicted by general relativity. And there is no other expected source of quadrupolar correlations that would be able to mimic a gravitational wave signature. Something like a reference clock error at the observatory would have a correlated signature between pulsars, but it would be monopolar. Something like an incorrect solar system ephemeris to account for local solar system gravitational effects would have a dipolar correlation. And so this quadrupolar correlation pattern is the smoking gun of a gravitational wave in pulsar timing data. To detect this requires regular monitoring of dozens of very high precision pulsars over time periods of years. And that is exactly what the NANOGrav project does. And we are able to predict the arrival times of pulses to on the order of tens to hundreds of nanoseconds over that 10-year period, which in and of itself is an amazing thing. So our observing program primarily uses the Greenbank telescope and the Arecibo Observatory to observe currently about 39 pulsars in each location with monthly cadence, although we also have higher cadence programs at each observatory as well. It goes without saying that we're obviously very concerned about the damage at Arecibo, and Arecibo is a vital observatory for Greenbank, or for the NANOGrav collaboration in addition to Greenbank. And so we fully support all the efforts of the National Science Foundation and the management team at Arecibo to bring it back to working order as quickly and as safely as possible. In addition to the GBT and Arecibo, we also have timing programs at the Very Large Array. And through a collaboration with the CHIME Pulsar team, we do regular monitoring of all NANOGrav pulsars, which are within the sensitive declination range of CHIME. And that's particularly useful for monitoring interstellar medium effects. NANOGrav is committed to regular data releases, and this plot shows the evolution of the number of pulsars that have been included in the array. Many of these are newly discovered pulsars from both large area and targeted surveys. Today, we're going to be hearing more about the 12.5-year data release, which is the most recent fully processed data release. We have the 15-year data release, which is undergoing further analysis as we speak. And so we should be seeing results from that in the not too distant future. And as far as the 12.5-year data release is concerned, we have 3 papers. All of them are available in the archive. The 2 papers that describe the actual timing data set, both a narrowband timing paper and a wideband timing paper, are now accepted. And the 12.5-year stochastic background gravitational wave search paper is just undergoing final review. I've listed the corresponding authors. These are full collaboration papers, but if you have any specific questions about any of them, then you can contact the individuals listed there. And at this point, I'm going to hand it off to Joe Simon, who is the corresponding author on the gravitational wave background search paper, to tell us about some of the results from that. So Joe, go ahead and take it away. And I will continue to advance slides here, so just let me know.
Thank you very much, Ryan. It's a pleasure to be here to talk with you all about our recent analysis of the 12.5-year data set, searching for a gravitational wave background. As Ryan previously said, the gravitational wave background induces a correlated quadrupolar perturbation across the entire pulsar timing array. The signal is embedded in our entire data stream, and so we need to search for the signal and all of our noise processes at the same time. And so what we are able to do is we're able to harness that quadrupolar perturbation and search for that in particular. And that is the definitive evidence that we are searching for, that there is a gravitational wave background in our data set. So the correlated perturbations are based on the angular separation between the pulsars on the sky. And what I'm showing here is a map of 3 sources on the sky, and you can see where the cross correlation between them appears on this quadrupolar correlation pattern, which is also commonly referred to as the Hellings and Downs curve, as it was first published by Hellings and Downs in 1983. And so if we then create a cartoon correlation matrix for these 3 demo pulsars, what you can see is that the autocorrelation term of this correlation matrix, so the diagonal piece, really dominates the amount of power that we're picking up in our array. And that's just due to the fact that these cross correlation pieces that contain the quadrupolar signal that we're looking for, they are just much smaller. The cross correlation coefficient is pretty small across most of the angular separations on the sky. And so we expect that the autocorrelation term, a uncorrelated process, will appear in our data before we'll be able to definitively detect spatial correlations. And so when we're actually searching in our data, we actually search first for an uncorrelated process, and then we do a series of model selections where we test for the evidence of a cross correlation in addition to an uncorrelated process. Ryan, you can go to the next slide. So one of the different tools that we incorporated in this analysis is that typically when we've been searching for a gravitational wave background, we have been modeling it as a power law, and we have been using 30 independent frequency bins to model that power law. This was chosen based on trying to make sure that the upper limits that we were setting in previous data sets were not sensitive to the number of frequencies that we chose. However, what you can see here, shown in the green curve here, that standard 30 frequency power law is being impacted by some excess noise at higher frequencies. Now, this higher frequency excess noise is not the gravitational wave background. And so what you're seeing is that we're actually not able to pick up and correctly characterize the low frequency noise when we incorporate that model. So what we've instead chosen to do is we have moved to just searching in the lowest frequencies, which is where we expect the majority of the signal to be for a gravitational wave background. Ryan, you can go to the next slide. And so the first thing that we do, as I said, is that we test for the significance of the presence of an uncorrelated common spectrum process. So this is just looking at the auto terms in that correlation matrix. And we model that assuming a power law model. And what we found when we do that search on our latest data set is we find really strong definitive evidence for the presence of a common spectrum process. It has closed contours on our amplitude. In the past, there was some concern about incorrect modeling of the solar system ephemeris, and we have a ephemeris uncertainty model that we incorporate. It's called Bayes FM, and even when we incorporate that, we still recover definitively strong evidence for the presence of this common spectrum process. So this is the first time that a pulsar timing array data set is seeing strong evidence for low frequency common spectrum noise. You can go to the next slide. The next step is to then search for the presence of a cross correlation of any spatial correlations with this common spectrum process. When we do that, we do not find strong evidence for the Hellings and Downs curve, so for that quadrupolar process. So the data is uninformative in terms of whether or not there is a quadrupolar present. So we cannot definitively say whether this process is a gravitational wave background or not. But we do search for other correlated processes. We search for a monopolar process, which, as Ryan said, is what we expect if there were uncertainties in the clocks. And we also search for a dipolar process, which is what we would expect to find if there was some unmodeled uncertainty in the solar system ephemeris. And in both of those cases, we find definitive evidence against the presence of either a monopolar or a dipolar process being thus that is associated with this strong common process that we are finding. So we're in this this kind of interesting spot where we can't definitively say what the cause of the process is, but we can say what the process is not. If you go to the next slide. We also search for multiple processes, and the data isn't informative either way. So it is unclear if this common spectrum process is a single process that we're picking out, or if there are multiple things present in the data. If you go to the next slide. So all of those searches included the entire correlation matrix, so both the auto term and the cross term. And the amplitude that we are recovering in those searches is dominated by the power that we're seeing in the auto terms. And so there's a different analysis that we do that searches only in the cross terms. So we completely ignore the auto term and just look for the presence of a signal in the cross terms. This is analysis. It's called the optimal statistic. Excuse me. And so when we do that, we are finding that the evidence is comparable across a variety of spatial correlations. So again, we are not finding definitive evidence one way or the other for the presence of this quadrupolar signal that we're searching for. But as you can see here, when we compare to previous data sets, the sensitivity to this quadrupolar signal is increasing. You can see that the orange error bars are much smaller than the blue. And then the dotted line here is showing the best fit, the kind of expectation for the quadrupolar based on the amplitude that we are recovering in the auto terms. And if you kind of squint, you can kind of say, well, maybe, but it's clear that we don't have definitive evidence at this time. Go to the next slide. So as I said, the kind of headline takeaways here are that there is strong evidence for an uncorrelated common spectrum process. It is showing up in a majority of our pulsars. It has strong evidence. However, the source of this process remains unknown. So without conclusive, definitive evidence for the quadrupolar spatially correlated process, we can't say whether or not what we're seeing is an astrophysical background. However, we can say that that the potential for known systematic issues being the primary cause here, there's definitive evidence against that. Again, we can say what it's not, but we can't quite yet say what it is. So where do we go from here? And to answer that, you can go to the next slide. We've taken the 12.5-year data set and we have simulated a data set that is very, that has identical noise processes. And we've extended the baseline into the future. We have kept just the same 45 pulsars. We have filtered out the uncorrelated common process as best we can, and we've injected a variety of gravitational wave backgrounds at a bunch of different amplitudes. And what you can see here is that we expect that the significance of this Hellings and Downs quadrupolar correlated process, we expect that significance to grow with time. And so the red star here shows where we are currently at in the 12.5-year data set. The dashed red line shows the amplitude that we are currently recovering. And you can see that at the kind of 12-year baseline mark, we get something relatively similar to what we're seeing in our current data set. And it's strong evidence for the auto terms, but not yet definitive evidence for something in the cross terms. However, as we extend that baseline to 15 years and onwards to 20, you can see that that evidence strongly increases. And so if what we're seeing is indeed the first hints of an astrophysical gravitational wave background, then we expect that those cross correlation terms should grow pretty quickly in their significance, and we'll be able to say something really soon about whether or not this is indeed what we are seeing. Ryan, you can go to the next slide. And so there are currently data sets that are being curated throughout the International Pulsar Timing Array community. And as I said, those should be able to have definitive evidence as to whether or not what we are seeing is indeed the first hints of a background or not.
All right, thanks, Joe. So at this point, we will open up for some questions. If you could please use the Q&A feature on the Zoom webinar, and we already have one. So Pranav Ghosh asks, can you please tell us a bit more about the advanced noise models tailored to individual pulsars and the new descriptions of DM oscillations?
Absolutely, yeah. So this is ongoing work that we are employing here, and so one of the ways that we are trying to mitigate this excess high frequency noise is by modeling dispersion measure using Gaussian process, and so that would allow us to take the entire DM time series and use all of that information when we're predicting what the kind of chromatic structure of the timing residuals are. And in addition to that, currently, we use power law models for all of the intrinsic red noise. And there are a variety of other red noise models that we're currently testing, things that allow for deviations from that power law, specifically at higher frequencies. So things like a broken power law, things like a T process, where you've got an underlying power law, but it's allowed to be a bit fuzzy, so it's not quite so strict. And we are currently doing a series of kind of model selection tests to allow each pulsar's data to inform which model the data prefers. And when we do that, we do see that we are able to reduce the excess high frequency noise. And so that we should have more on that soon.
Okay, Dan McCammon asks, what are the likely sources of the autocorrelation signal?
Yeah, it's a great question. So the fact that it is a common spectrum, so it's the same amplitude and spectral index across all of the pulsars. It's really hard to come up with what that could be. Now we are dominated by the pulsars that have the longest observing baseline, so that there's about a dozen of them. And so it could be that we're starting to see similar intrinsic spin down noise across all of them. However, the fact that it's the same amplitude makes that unlikely. It could also be that there are other ephemeris issues and solar system issues, such as like planetary Shapiro delay, that we're not taking into account properly. but it could also be the first hints of an astrophysical background. Just that at this time, we can't quite distinguish between all of those possibilities.
Okay, David Roberts asks, the microwave background has a strong dipolar term. Why is this not expected for the gravitational wave background?
So gravitational waves, right, are quadrupolar in nature, and so the because of that, the kind of L equals 2 power term is the dominant term. That there are some higher order terms that come into it as well. It's not strictly a quadrupolar cross correlation. However, there's just due to the nature of what gravitational waves do to space-time, there is no monopolar or dipolar term.
All right, we'll have time for 2 more questions. So Ron Sayer asks, are there new radio telescopes coming online soon that will improve the measurement significantly?
Ryan, you might be best to take that question. I'm not an expert on radio telescopes.
Sure. So I will say that with existing facilities, we are developing a new receiver for the GBT, and we also hope to have one for Arecibo, similar to a receiver that was now in use on the Parkes telescope that gives us more instantaneous bandwidth. And this is going to improve signal to noise, but really help us do better characterization and mitigation of interstellar medium effects. And we expect that that will significantly improve our overall timing precision. We also have a new project to implement some advanced signal processing techniques at the GBT that will further help to mitigate these interstellar medium effects. So that's with existing facilities. Down the road, so there are international telescopes such as FAST and MeerKAT that are starting to contribute to timing data sets. And so we're very much looking forward to incorporating that data. And then telescopes like the NGBLA and the proposed DSA 2000 will give us more collecting area and more sensitivity, so we can add more pulsars to the array, and will give us presumably higher precision pulse times of arrival, which will also both be very important for advancing this into the future. And so I think we have time for one more question. So not all, this is kind of split into 2, so I'll just ask both. Not all pulsars are equally good sources. How do period irregularities manifest themselves in the auto and cross correlations? And then is there evidence for a population of more stable pulsars in the fainter pulsars?
I'm not an expert in pulsar population demographics, so I don't know about the second part of that question about whether or not there's more stable pulsars in the fainter pulsar population. But in terms of how individual pulsar timing noise manifests itself in these auto and cross correlation terms, that all of those model terms are included in our analysis, and so we believe that that in terms of the kind of timing model parameters, we have a series of white noise terms that capture any mismodeling that's happening on short timescales, and then we also have incorporated in our model in intrinsic red noise model for each pulsar. And so the auto and the cross correlation terms, they are a common process, and so it needs to be noise that has the same characteristics across all of the pulsars. And so if there's individual pulsars that have some amount of irregularity, some amount of excess noise, we have individual noise terms to capture those. And so if there's multiple pulsars that have similar kinds of excess noise, that can bleed into the common process. We expect that to primarily show up as kind of excess noise in the auto terms. However, we don't expect that to be the kind of dominant source of noise that is found in the auto terms, because again, it would need to be identical, and that there's no evidence that kind of individual pulsars have similar irregularities that could be kind of influencing a common process at this amplitude.
And I'll just briefly answer the other question. Certainly, you could have stable but faint pulsars, and next generation pulsar surveys, both with current facilities, but new instruments and future facilities, will be important for finding those. Obviously, the signal to noise of the pulsar that you get influences the time and precision. And so bright pulsars are always good. Also, more distant pulsars may suffer more from interstellar medium effects, but that's why we are building these new instruments to help mitigate those. So by continuing to add pulsars to the array, we definitely increase our sensitivity. And hopefully we find some other great timers out there. And so I think that that's where we will have to end it. So thank you again, Joe, for joining us and for that wonderful talk. And thank you to everyone for tuning in. And if you have any further questions, please feel free to reach out to Joe, myself, or any other member of NANOGrav. All right, goodbye, everyone.